really welcome to be here in the room, also more informal talks. They're not recorded, just to generate some discussion, post some questions, and then also use yeah, so that's all. And yeah, so now I should take off to probably.
I think you started already.
Okay.
Yeah,
okay.
I think so.
So then our first speaker will be Andreas Cap from the University of Vienna, who will talk about partial G-structures and partial Cartan geometry.
Thank you very much. So I'd like to start by thanking the organizers and in particular Katharina for inviting me to this program and bringing me to Cambridge for the first time in my life. Yeah, so let me get right into the talk. And although I have slides, of course, you are very welcome to ask questions, and I can use the board for answering if necessary. So this talk reports on joint work with my PhD student, Michael Vasilievich. And this joint work is about to be completed, and actually it grew out of his thesis work. And I'll say a bit more about that in the course of the talk. And so, yeah, Katharina also invited us to have some introductory aspects, and I will actually have quite a bit of introductory aspects. So I'll review the fundamentals of G-structures, the special case of AHS structures, and the equivalent description of AHS structures as Cartan geometries. And the thing I want to emphasize there is that both in the case of G-structures and in the case of Cartan geometries, there is quite a bit of algebra going into the geometric considerations. And viewing things in the right way, the generalizations that I will talk about are pretty straightforward in some sense. And so getting the right view on the classical concepts is an important part of the story. Okay, and then I'll outline this more general setting. And actually the best way to describe this is think about the foliation and think about structures on every leaf of that foliation. That depends smoothly on the leaf, if you want. And it turns out that this is much easier, or as easy as thinking about families of structures in the sense of you take the total space of a local trivial bundle and a structure on each fiber or something like that. This situation of leaves of a foliation will be as easy to deal with. And the key feature of the whole story is that you can use all the algebra that was developed in the study of the original structures without any change in this case of families. So all the results like existence of canonical Cartan connections and all these things generalize in a more or less straightforward way. And that's the main topic of the article that we are writing. And in the last part, I will outline an application. Namely, this also leads to a version of the BGG machinery for partial Cartan geometries that come from partial AHS structures. And this nicely combines the classical BGG approach for AHS structures with the relative, so the approach to relative BGG sequences that I have developed in joint work with Vladimir Socek. And it brings this picture of the relative situation more to the picture of BGG resolutions along a fiber, which was introduced in the book of Baston and Eastwood on the Penrose transform and Twistor theory. So I get a nice connection to the title of the program here. All right. So as I said, most of my talk will be this review of G-structures and Cartan geometries. So let's get started with that. So the idea of a G-structure is very easy. You just try to put some kind of structure, in quotation marks, on each tangent space of a manifold in such a way that all these structures are isomorphic to some standard structure. So say, for example, if you put a non-degenerate bilinear form on each tangent space, you want all these forms to have the same signature. You don't want degeneracy or something like that. So you have a standard model on Rn. And the explicit description of these structures can look very, very diverse. So I already mentioned an inner product. You can have a subvariety in each tangent space or in the projectivization of each tangent space. Or you can do things like, say, I decide to view a vector space of dimension k times L as a tensor product of a k-dimensional and an L-dimensional space. And in that language, it's not entirely easy to say what this means, but there is a simple uniform approach. And this is based on, you start with a closed subgroup in GLNR. So in the case of an inner product, this would just be the orthogonal group of the inner product. In the case of a subvariety, it would be those linear automorphisms that map this subvariety to itself. Here, it would be just a subgroup coming from GLK times GLN in GLK times L. Sorry, K, L, L, yeah. Yeah, and you should think about this closed subgroup G0 as the maps that preserve this model structure. And then you don't really have to decide what the model structure is. It suffices to know its automorphisms. And then the formal definition of a G0 structure is as a reduction of structure group of the full linear frame bundle of the manifold to this group G0. Yeah. I should also say, I don't know, maybe I'll say it later again. In several applications, it is preferable to also allow coverings of closed subgroups of GLNR to have something like spin structures included. And this actually causes very little problem. So that's a very simple generalization. In any case, such a structure comes equipped with a principal G0 bundle, which in particular means that any representation of G0 gives rise to a natural vector bundle by forming associated bundles. And even better, if you have a principal bundle, this bundle always admits principal connections. So we have principal connections on this principal bundle, and these are referred to as connections compatible with the G0 structure. And again, in terms of the explicit description of the structure, it may be pretty complicated to say what it means to be compatible with the structure, but there is a very simple uniform concept that you have here, and you can make this explicit in any case you're interested in. Okay. Now, by construction, because you have constructed it as a reduction of structure group of the linear frame bundle, the tangent bundle Tm is associated to this given principal bundle P. So whenever you have such a connection, principal connection on P, you get a linear connection on the tangent bundle. And as I said, this respects the G0 structure, whatever this means. Yeah, in the case of an inner product, it's very easy. It just says that nabla G is 0. But for these tensor product things or stuff like that, it may be much more complicated. But there is a conceptual approach of how to understand what this really means. The important point here is that as a connection on the tangent bundle, this nabla has a well-defined torsion, and this is kind of the crucial ingredient in the theory of G structures. Namely, if you look at principal connections on a principal fiber bundle, it's very easy to understand them as an affine space. Yeah? So the difference of two principal connections is just in a horizontal equivariant one form. And then you can check how this change of connection influences the change of torsion. And it turns out that this comes from a very simple linear algebra guy, which is called the Spencer differential. And I denoted it here by del S because it has connections to Lie algebra cohomology. And this maps linear maps from Rn to G0, and G0 is the Lie algebra of my group G0, to skew-symmetric bilinear maps from Rn times Rn to Rn. And my G0, since I have a covering of a closed subgroup, this G0 is just a Lie subalgebra of the Lie algebra of n times n matrices or linear maps from Rn to itself. And this Spencer differential is extremely simple because since G0 consists of linear maps, if you have a linear map from Rn to G0, you can consider it as a bilinear map from Rn times Rn to Rn. And then you can just alternate this bilinear map. So that's the explicit formula. Yeah, phi of x is a linear map. You apply it to y. minus phi of y, which is again a linear map applied to x. Okay. And more importantly, these are representations of the group G0, yeah, because Rn is, because it's a closed subgroup or a covering of a closed subgroup. And G0, of course, is a representation under the adjoint. And this differential is G0 equivariant. So you even get a connection to representation theory of G0 here. And this is pretty important. And the key fact here is that if you pass to associated bundles, then this del S computes the change of torsion caused by a change of connection pointwise in a way. Yeah, so in terms of sections of associated bundles, the principal connections are affine over the bundle induced by these representations. So you can relate two connections by a section of that bundle. And then the relation between the torsions is just by the tensorial operation induced by this del S. Okay, and of course this tells you that if you understand this linear map between two finite dimensional vector spaces, you get important information on the properties of G0 structures for the fixed group G0. Yeah, and in particular, injectivity and surjectivity of this map have obvious direct consequences. So first of all, you can take the co-kernel of this map. So you take the target space, factor out by the image, and then this induces a quotient bundle of lambda 2 T star M tensor Tm, obviously, because it's a representation of G0. And if you take the connection, if you take the torsion of any compatible connection and project it to the quotient, then by construction, this is independent of the choice because you have factored out everything that changes. And this defines a fundamental invariant of the structure, which is called the intrinsic torsion. Okay. And then vanishing of this intrinsic torsion is equivalent to the existence of a torsion-free connection that is compatible with your G0 structure, which in the theory of G structures is often referred to as integrability, which is kind of a, yeah, difficult terminology, but it's common. And in particular, you always have a torsion-free compatible connection if del S is surjective. And this is the case, for example, for Riemannian matrix or pseudo-Riemannian matrix, in which del S actually is a linear isomorphism. Okay. So on the other hand, if you look at the kernel of this Spencer differential, and I'll denote this by G01, this is what is classically called the first prolongation of G0. And now if you take a compatible connection, look at its torsion, then the space of all compatible connections with the same torsion by construction is an affine space modeled on sections of the bundle induced by this G01. Yeah, so you get an immediate description of all compatible connections with fixed torsion. And so in particular, if this first prolongation vanishes, you can try to obtain a canonical connection on each G0 structure by normalizing the torsion in some way. Okay. However, normalizing the torsion is also an interesting question in the case where this first prolongation is non-trivial, because then it leads to families of distinguished connections rather than a single distinguished connection. Okay, so that's the next thing I want to talk about, normalizing torsion. And as I said already, this is also relevant if the first prolongation is non-trivial, because then you get families of preferred connections. Now, the obvious idea what you can do is if you want to normalize your torsion, now, maybe I don't need a drawing here. Ah, okay. So if you think about the space of possible torsions, and then somewhere you have the image of Spencer differential. So that's how torsion moves. So if you want to normalize, what you have to do is you have to choose in some way a complementary subspace, because then wherever you land, you can move it uniquely into that subspace. And so this is like what I will denote by N. So the obvious idea that you have is you can choose a linear subspace N in lambda 2 in linear maps from lambda 2 Rn to Rn, which is complementary to the image of the Spencer differential. And of course, this can always be done. However, while our things are pointwise, in order to be really able to go to associated bundles, you need a complement which is G0 invariant, and then you can really normalize. And actually here you meet a pretty non-trivial algebraic question, because existence of a G0 invariant complement is not guaranteed in general. And actually finding some complements is often the major difficulty in describing these geometric structures. Okay. But once you have a G0 invariant complement, it gives rise to a subbundle of TM value 2 forms. And then on any G0 structure, there are compatible connections whose torsion has values in that subbundle. And if the first prolongation vanishes, then this connection is unique. And so you obtain, once you've chosen this normalization condition, so that's the terminology here, then you find a canonical linear connection on the tangent bundle of any manifold endowed with a G0 structure. And I mean, in everyone's favorite case of Riemannian geometry, all this is trivial because, as I said, in this case, this del S is a linear isomorphism. So its image is everything. A complement to everything is nothing. So it's just a 0. And the first prolongation vanishes. So you get a unique torsion-free connection on any Riemannian manifold. And somehow that's where Riemannian geometry starts, because then you can start analyzing the curvature of this connection. And of course, you can do this in general, provided that you have canonical connections. Okay, right. Yeah. The condition that this first prolongation vanishes can be equivalently phrased nicely in terms of automorphisms or morphisms of G0 structures. Namely, the condition that this first prolongation vanishes is equivalent that whenever you have a morphism and you have a point, then locally around that point, the morphism is determined by the one jet in that point. So this is a well-known fact from Riemannian geometry, because you know that any isometry maps geodesics to geodesics, and the geodesic is uniquely determined by its direction. So if you know where the point goes and where the direction goes, you know where the geodesic goes, and therefore you know your isometry locally around that point if you know its value and its derivative in that point. Okay? And yeah, the opposite end of the spectrum are structures of infinite type, like symplectic structures or almost symplectic structures, for which in general no finite jet suffices to determine an automorphism locally. And again, this can be rephrased in a purely algebraic fashion, namely, similar to the first prolongation, you can define higher prolongations, and algebraically this just means that all these higher prolongations are non-trivial. Okay, so there is a purely algebraic thing. It's just that this relation to jets of morphism gives you a geometric understanding of what these algebraic conditions mean. Okay, and now I'll move to this so-called AHS structures, or almost Hermitian symmetric structures, or abelian parabolic geometries, however you want to call them. And the basic for their importance is a classical result by Kobayashi and Nagano. And this is under an assumption which may look slightly unnatural here. Namely, you have to assume that G0 acts irreducibly on Rn. So you assume that there is no subspace in Rn that is invariant under your group G0. And under this assumption, this general result of Kobayashi and Nagano kicks in. And namely, they say there are exactly 3 cases in this situation that G0 acts irreducibly. First of all, it may happen that the first prolongation vanishes. Second, it may happen that your structure is of infinite type. Third, the first prolongation is non-trivial, but the structure still is not of infinite type. So some higher prolongation vanishes. And then it turns out that the only examples for which this is the case are the AHS structures. And there, much more deep algebra starts kicking in. Okay, so examples of these AHS structures, most importantly, conformal structures in any signature. They exactly have the property that any conformal isometry is determined locally around the point by its 2jet, but not by its 1jet. And other nice examples are almost Grassmannian and almost quaternionic structures. And the list in general is pretty short. Yeah. Maybe I should say a few words about these irreducibility assumptions to those who know the story. So if you don't know the story roughly, then don't listen. It will just be confusing. The point is, once you have an invariant subspace, this corresponds to an invariant subbundle in the tangent bundle. And then the properties of the geometry completely depend on integrability or non-integrability properties of this subbundle. Yeah, just think about rank 3 distributions in dimension 6. They may be involutive, infinite type. They may be generic, finite type. Yeah, so you cannot hope to get anything out of pure algebra in this case. Yeah, so that's why this assumption of not having any invariant subspace is kind of natural, because once you have an invariant subspace, you have to distinguish its integrability or non-integrability properties, which means in the language of G structures that you have to start studying the intrinsic torsion and kind of do a finer analysis based on properties of the intrinsic torsion, and then you would run into things like parabolic contact structures or generic 2, 3, 5 distributions and so on and so forth. Okay, right. So back to the description of these AHS structures. And the amazing point about this is they just started from G structures, closed subalgebras of GL and R, and suddenly simple Lie algebras come into the game. And that's exactly what happens. So the general descriptions of these AHS structures is you take a simple Lie algebra, you endow it with a decomposition, so-called one grading. G is G minus 1 plus G0 plus G1 as a vector space, in such a way that this decomposition is compatible with the bracket. Yeah, which just means that G minus 1 and G1 are abelian. G0 acts on each summand via the bracket. And there is an additional bracket which encodes the structure somehow between G minus 1 and G1 going to G0. And such decompositions are completely classified for almost 100 years because they correspond to Hermitian symmetric spaces. And then if you choose any group with that Lie algebra, then you can define a subgroup G0 in there by the fact that the adjoint action respects the grading. Yeah, so you take all elements in G whose adjoint action is compatible with this grading. It turns out that this has Lie algebra G0, and it acts irreducibly on G minus 1. And this actually gives you the relation to G0 structures. So this group G0 has Lie algebra G0. The adjoint representation is a covering of a closed subgroup, so we're in the lane of G structures, and therefore we can talk about G0 structures in dimension n. Okay. Right. Yeah, and n is just the dimension of G minus 1. And maybe I say for the favorite example of conformal Riemannian structures, this Lie algebra G is SON plus 1, 1. And G minus 1 is isomorphic to Rn. G1 is isomorphic to Rn dual. And G0 is just a conformal algebra. Yeah, so in a way, it's also completely surprising at that stage how the semi-simple Lie algebra SON plus 1, 1 pops up from conformal geometry. Of course, once you know that the homogeneous model is the sphere and that the group of conformal isometries of the sphere is SON plus 1, 1, it's less surprising. Yeah, but if you just start from G0 structures, it would be pretty complicated to arrive at this picture. Okay. Yeah. We have to exclude two cases here. So SL2 is completely degenerate in a way. And we have to exclude a specific grading of SLN with n greater or equal to 3, which is, yeah, can again write this up easily. So basically, if you think about the gradings of SLN, they are very easy to describe. Such a grading is just given by decomposing matrices into blocks. And you can take the blocks to be of size k and n minus k. And things become slightly exceptional for k equals 1. Because, yeah, so I should say what the grading looks like. So then this is just G minus 1, G0, G0, G1. And the grading properties immediately follow from computing with block matrices. That's very easy. But you can see that for k equals 1, this becomes a bit exceptional because G0 becomes isomorphic to GL. Yeah, n minus 1R. If you start with SLN, yeah, and you see if G0 is GLN, this does not give an interesting G structure. Yeah, this gives the non-structure in a way. Okay, so we have to avoid this grading of SLN for which G0 is GLN minus 1. Although, as we shall see, this is of big interest because it gives rise to projective structures, but it doesn't fit into the picture that I'm developing here. But I'll discuss later how to bring it into that picture. So, and then the remaining 1 gradings give rise to these AHS structures, which are exactly the remaining entries on the list of G0 structures of Kobayashi and Nagano. And so what happens is if you use the Lie algebra structure of G, yeah, so actually if you want to see why the first prolongation is non-trivial, you can write this out immediately in terms of the Lie bracket of G. And you can see that G1 actually sits inside the first prolongation of G0, and avoiding these cases, it equals the first prolongation of G0. And you can prove that G1 is isomorphic to the dual of G minus 1, and that the higher prolongations of G0 are trivial. Yeah, that's all very easy from the fact that G is simple and using the Lie algebra structure of G. So you see that this actually corresponds to a case of finite type with non-trivial first prolongation. And the Kobayashi-Nagano result tells you that this is everything. Okay, and one can also use the Lie algebra structure on G mixed with ideas from Lie algebra homology and Lie algebra cohomology to construct an explicit normalization condition for torsions. And so you see that AHS structures always come with a family of preferred connections. And since this first prolongation is isomorphic to the dual of G minus 1, you see that these preferred connections always form an affine space modeled on one forms on the manifold. Yeah, so you always have a family of preferred connections that have normalized torsion and are affine over one forms. Yeah, and I should maybe say what happens in the case of in the favorite case of conformal Riemannian structures. There, of course, the normalization condition is boring because it's easy to see that the spans are differentially surjective, so you always have compatible torsion-free connections. And the obvious idea would be you take the Levi-Civita connections for the matrix in the conformal class, but that's not quite general enough because there are torsion-free connections that are compatible with the conformal structure beyond these Levi-Civita connections, and these are the Weil connections. And the Weil connections, and that's the definition of Weil connections actually, that they are compatible with the conformal structure and torsion-free. And for the Weil connection, it's easy to see that they are really affine over one forms, whereas the Levi-Civita connections of the matrix in the conformal class are affine over exact one forms. Okay. And now it turns out that you can associate to such an AHS structure a canonical Cartan geometry. And actually, depending on your approach, you can view this Cartan geometry as encoding these preferred connections. So what you do is you start with your AHS structure, you go to the space of all preferred connections, and you endow that space with a Cartan geometry. Okay, so let me explain this a bit more. So first of all, we need the group P, and which shows up in the homogeneous model of the Cartan geometry. So we take G0 plus G1, and we take the normalizer in G of this Lie algebra P, G0 plus G1. So in particular, it's visible that this subgroup G0 is contained in P, and it's easy to see that P has Lie algebra P. However, the more natural point of view is that G0 can be viewed as a quotient of P, and it turns out that the subgroup by which P has to be quotiented, this is just, I mean, you can easily describe it as the exponential image of G1, which happens to be a closed subgroup. But the conceptual point of view is, so if you look at G mod P, G acts from the left, you have a base point. On that base point, this is fixed by P. So you get an isotropy representation of P on the tangent space of the homogeneous space at that base point. And G0 is exactly the image of P under this representation. Yeah, so that's what you see to first order on G mod P, if you want. Okay, and so this last statement that actually you have this kernel of the isotropy representation easily implies that G mod P carries a natural G0 structure. And now what the Cartan description tries to do is you want so G to G mod P is a principal P bundle. This carries a nice object, namely the left Maurer-Cartan form, and you are aiming for a parallel description for arbitrary G0 structures. And so what you can do is the following. If you start with your G0 structure, it comes with a principal G0 bundle. Then you have the compatible connections that can be described in terms of connection forms. So you can attach to each point U in P the values at U of the connection forms of distinguished connections. Okay? And it turns out that this is a finite dimensional space, which is isomorphic to G1. And then you just play a bit with algebra and you find out that you can nicely make the result into a principal P bundle. And now you can see that this principal P bundle already comes with quite a few tautological forms. So first of all, P is a reduction of structure group. This can be equivalently described by the existence of a canonical strictly horizontal equivariant form with values in Rn, or in this case, you get a tautological 1 form with values in G minus 1 on P. You can pull that back to G, which is an extension of P. Moreover, the points in G are values of connection forms. So if you have a tangent vector, you project it down, you insert it into the connection form, you get something in G0. So from this construction, you get a tautological G0 valued form on G. And so we have something with values in G minus 1, we have something with values in G0. Question is, can we extend it? So then we can ask yourself, is it possible to extend this to a P equivariant form with values in G? And then by just dimension counting, and of course you would require that this reproduces the generators of fundamental vector fields, as you want it for a connection form. And then by a simple dimension count, you see that if you're able to do that, then necessarily omega has to be a linear isomorphism on each tangent space. Okay. Right. And yeah, if you think about this, in this case, it's obvious that this can be done in each point. It's not at all surprising that this can be done smoothly because all the ingredients are smooth, but there obviously is a complete freedom of choice here. Yeah. So the things about the G1 component, the only thing that you have fixed is what it does to fundamental vector fields. So you need some additional condition in order to pin this thing down uniquely. And that's again where algebra kicks in. So what you have to do is you have to again select the normalization condition, which now lives on a different space or on a bigger space. So actually, what you can do is you can form this curvature of the Cartan connection, which just is the failure of satisfying the Maurer-Cartan equation. And so this curvature is a section of the associated bundle corresponding to linear maps from lambda 2 G minus 1 to G. Yeah, I mean, this needs a bit of information, namely that this curvature is automatically horizontal. So therefore it descends to entries from G minus 1, and then the values are in G. And you see, so this actually naturally projects onto L lambda 2, G minus 1, G minus 1. And this is where our normalization condition for the torsions actually set. And what we really did was just we restricted the normalization condition for the curvature that one can find using algebra to this subspace. Okay. So actually, again, using the Lie algebra structure on G and ideas from Lie algebra homology and cohomology, you can derive a normalization condition. So there is again a map delta here, which is in this case then really a Lie algebra cohomology differential, and you need an invariant complement and even a P invariant complement to its image here. And you can do this using Lie theory. Okay, and so then this pins down this omega uniquely, and it turns out that the pair G omega is unique up to isomorphism. And so you have really extended, you have constructed from an AHS structure a canonical Cartan geometry. Okay, so now, okay. Not yet. Once you have this canonical Cartan geometry, there are immediate consequences. So for example, if you look at the automorphisms of an AHS structure, they are equivalent to automorphisms of the associated Cartan geometry. And for the associated Cartan geometry, it's easy to use results on transformation groups to prove that these automorphisms form a Lie group. and the dimension of this Lie group is bounded by the dimension of the total space of the principal bundle, which equals the dimension of G. Yeah, and you also get results in a way that all invariants of the geometry can be derived from this Cartan curvature and things like that. So there are lots of general results that you can apply at this point. Okay. Yeah, so I want to say a few more words about this these exceptional grading and projective structures, because actually they fit very nicely into the picture once you have the Cartan description at hand. So if you take this grading of SLN that we had here, so it's like this. Okay, so this is just Rn, this is Rn dual, this is GLN minus 1. You still get a group P, as in the other cases. You can define Cartan geometries of type GP. There still is a normalization condition. You still can look at normal Cartan geometries. And it turns out, you see, for the other geometries, we constructed the Cartan bundle via the connection forms of distinguished connections. Here, the underlying bundle is the full frame bundle of the manifold, and you can think about such a normal Cartan geometry as encoding a class of distinguished connections. And this class of distinguished connections are torsion-free linear connections on Tm, and they are affine over 1 forms. And it turns out that there is a very nice geometric description of the resulting class that you can derive from general ideas about Cartan geometries if you want. Namely, it's a projective equivalence class of connections. And projective equivalence here means that, so two connections are projectively equivalent if and only if they have the same geodesics up to parametrizations. So in this case, the normal Cartan geometry is not an equivalent encoding of a G structure, but it's an equivalent encoding of a projective structure which consists of the choice of a projective equivalence class of connections on a manifold. And then it turns out once you're in this Cartan picture, then most of the results on AHS structures that are derived from the Cartan description extend to projective structures. So this refers to all these things like trajector bundles, trajector connections, distinguished curves. All these things can be generalized without problems. Yeah, also BGG machinery and things like that. Okay, so finally I come to the things which are in the title. So what's the generalization? And it's really, I mean, this part will really be relatively short because once one has the right picture, the generalization is easy. So now what we do is we start with the description or with the analog of G0 structures. So we fix a subgroup, yeah, and again, it may be a covering of a subgroup without problems. But now we consider a manifold of dimension which is at least n and an involutive distribution in the tangent bundle of rank n. Yeah, so if M has dimension n, this is just the full tangent bundle and we recover standard G0 structures. But then, of course, for this distribution, there is a frame bundle, which is a principal bundle over M with structure group GLNR. And now you can define partial G0 structures as reductions of structure group of that frame bundle. No problem. Equivalently, you can take an abstract principal G0 bundle, which is endowed with an appropriate partially defined 1 form. And so this is something that will occur throughout in what follows. So what do I mean by partially defined differential forms? So you have this distribution on M, you can lift it to P, and I denote this by F tilde, and you observe that this is invariant under the principal right action. So now you can take the bundle L F tilde Rn, which means exactly Rn valued 1 forms, which are only defined on F tilde and not on all of the tangent space, and one requires that one has a one form in there, which is G0 equivariant, which makes sense because this is invariant under the principal right action, and such that the kernel in each point is the vertical subspace. Yeah, and this is exactly the counterpart of what you usually call the strictly horizontal invariant Rn valued one form. No, it's not required at that point. It's only required if you want to get non-trivial results. Yeah, so the definition definitely makes sense for arbitrary f, but if you want to define torsion, if you want to get curvature, you need involutivity. Yeah, so I mean, I don't know whether there is something interesting outside of involutive cases. No idea. Okay, and now, of course, if you have this involutive distribution defines a foliation. If you take a leaf of this foliation, then this leaf has dimension n, of course. And it's very easy to see that if you have such a partial G0 structure, you get a standard G0 structure on L. So you get a smooth family of structures on the leaves of the foliation. And locally, this just means you get a codimension parameter family of smooth structures in a naive sense. But of course, there are interesting global aspects. Yeah? So if you think about, there are foliations which have a dense leaf. So then if you have such a partial structure, then globally it's uniquely determined by the induced structure on this dense leaf and things like that. So I mean, not that these things have been explored yet, but I think there's quite a lot of interesting stuff going on. Okay, and if you say I don't like groups, I don't like principal bundles, I don't like all this junk, the definition can be easily made explicit in any case. So for example, if you think about the case of conformal structures, so you take G0 to be CON, then a partial G0 structure can be simply described as a conformal class of positive definite bundle matrix on this involutive distribution. Yeah, and whenever you know an explicit description for a G0 structure standardly, then you can convert this into the partial situation rather easily. Okay, so what you have to note is that morphisms of such partial G0 structures are much richer than morphisms of ordinary G0 structures. Because more or less by definition, if you talk about G structures, you require a local diffeomorphism on the base and some lift to the total space of the principal fiber bundles. Here, this local diffeomorphism condition is not necessary. So if you have two such structures, you can talk about principal bundle homomorphisms, and the requirement that you need for the base map is that for each point here, the tangent map restricts to a linear isomorphism from F1 in the point X to F2 in the point phi of X. Yeah, but outside, so you need that the distributions are preserved. You need that on the distribution, it restricts to a linear isomorphism. But what happens outside of the distribution is completely irrelevant. And once you assume this, you can form the pullback of θ2 along this principal bundle homomorphism phi, and you call phi a morphism if phi star θ2 equals θ1. Okay, so there is a much more wide class of morphisms. So in particular, if you want, this inclusion of a leaf can be thought of as a morphism of partial G0 structures. Yeah, so the inclusion of a leaf with the induced G0 structure defines a morphism of partial G0 structures. Okay, so in particular, they can have different dimensions. And of course, automorphism groups can be infinite dimensional. Just think about, take Rn times Rk or something like that. And the flat structure on Rn, this may have few automorphisms, but then you can combine it with any diffeomorphism of Rk. What remains true, however, is that, I mean, this description on the level of the principal bundle is purely technical. Actually, you would like the morphism to be something defined on the manifolds. And this cannot be completely true in general, as you see for spin structures. But it remains true here that the automorphism phi, it's even a morphism, not only an automorphism, is uniquely determined by its base map up to a locally constant function. Yeah, so the freedom in lifting base maps to morphisms is still very small. And again, where this locally constant function has its values is determined by group theory. So it's something that you know in advance. Yep, yeah, that's fine. No problem. It's still everything is determined by its base map up to a discrete freedom. Okay, so that was already the story about partial G0 structures, and actually partial Cartan geometries are as easy. So you start with G and a closed subgroup P, and you start with a pair MF, where the rank of F is the dimension of the homogeneous space G mod P. And then you can take a principal P bundle G over M, and you again have the lift of the distribution to TG. And now you define a partial Cartan connection in the obvious way. So you take a section, so a partially defined one form with values in G, which is equivariant in the obvious sense, reproduces the generators of fundamental vector fields, and whose values in each point are linear isomorphisms. That's it. So that's the definition of a partial Cartan geometry. And morphisms, again, can be defined in the obvious way, and you only need the weak restriction on the base map that we had before. So it's only the behavior on the distribution of the base map that plays a role. Everything else is irrelevant. So in particular, there can be morphisms between partial Cartan geometries of different dimensions without any problems. Okay, and now I mean, this story about underlying G structures of Cartan geometries definitely can be done in a more general setting, but I'll restrict to the AHS case here. So if I'm in an AHS situation with G0 and P and G, and you start with a partial Cartan geometry of type GP, then this produces an underlying partial G0 structure. Namely, what you do exactly the same thing that you know. So you take the quotient of the principal bundle G by P plus, and this P plus is the subgroup of P such that G0 is canonically isomorphic to P mod P plus. So this becomes a principal fiber bundle with group P mod P plus, which is G0. And you can take the values of omega and project to G minus 1, which is isomorphic to G mod P. And then you find out that the resulting partially defined form descends to P and makes it into a partial G0 structure. So that's completely straightforward. And then it turns out that if you use the right construction for canonical Cartan connections, then they extend to partial structures without too much change. So the first important bit is the involutivity of F. I said that already in answering Arman's question. So this allows you to define, in particular, the curvature of a partial Cartan connection. And this curvature is a partially defined two form with values in G. And so you can use the usual normalization condition because this bundle here is induced by LG minus 1G. This bundle here is induced by L lambda 2G minus 1G, and so on and so forth. So you can just use the usual normalization conditions. And you also have the geometric interpretation if you prefer the construction via distinguished connections. So you can do the construction based on partial principal connection forms. They are equivalent to partial linear connections, which are defined on the distribution F. and allow differentiation only in F directions. And such a partial linear connection has a torsion that you can define by the usual formula using that F is involutive. And so you can use the same normalization condition as before to define distinguished partial connections. You can attach them to each point. You can make this into a principal bundle with the right group. And all the computations can be used from the standard construction, more or less. And then you again have tautological forms, and you uniquely extend them to a Cartan connection that satisfies the normalization condition in the curvature. So the equivalence goes through. Okay. Yeah. Now this description here via connection forms and connection immediately shows that this is functorial. Yeah, because if you have a morphism of G0 structure, you pull back a principal connection, you get a principal connection, this corresponds to the pullback of the linear connection, everything is compatible. So you see that this construction is functorial, and therefore gives you a categorical equivalence between partial AHS structures and normal partial Cartan geometries. In fact, there is a much better result, because this is like, in order to understand the equivalence, you have to go through the construction. And if you have something that produces a Cartan connection from other things, you have to start worrying with, does this agree with what I have constructed, and blah, blah, blah. And this gets very complicated. Here, there is the same strong uniqueness result that you get for AHS structures and parabolic geometries. Whenever you have two normal partial Cartan geometries and you have a morphism between the underlying structures, this uniquely leads to a morphism between the Cartan geometries. So in particular, you know, whenever you give me a normal Cartan connection, it's the one I have constructed up to isomorphism. Okay. Yeah, and now I can say a few words about what Michael did in his thesis. Namely, there is also a partial version of projective structures, which is not surprising after everything I've said. And they again can be equivalently described in terms of a normal partial Cartan geometry. And as I will say in the last 30 seconds, this leads to BGG sequences. And this situation is studied in Michael's thesis. And the surprising thing is that this occurs in very unexpected situations. Because what happens is, if you take any contact manifold, you take any involutive Legendrian subbundle of that contact manifold, then you get canonically a flat partial projective structure corresponding to this involutive subbundle. And so since this structure is flat, you get partial BGG resolutions just for one involutive distribution. So in particular, if you just have one involutive Legendrian subbundle on a contact manifold, you get differential operators of arbitrary high order that are canonically associated to this geometry, and partial BGG resolutions coming from that. And they generalize the relative BGG sequences of Legendrian contact structures in which you have a second Legendrian distribution. And it turns out that these relative BGG sequences, actually in the case that one of the distributions is involutive, do not depend on the choice of the complementary distribution, but are already intrinsic to one distribution. Okay, so as I said, I've got 30 seconds. Now, I mean, it's not, you see, for those who know how BGG works, they can now see that you can do BGG in this situation without problems. For those who don't, they won't learn it in the following 30 seconds. So I just say briefly, so what you can do once you have the Cartan description, you can take representations of G, restrict them to B, look at the associated bundles. These are partial tractor bundles. On them, you get a canonical partial connection. more or less by the usual construction. This can be extended either to a partial covariant exterior derivative or more nicely to a partial twisted exterior derivative, following what you do for relative BGG. Yeah, the codifferential goes without problems because you just have the same associated bundles. You have the homology bundles for which you know the associated, the inducing representations. Yeah, and then you do the BGG construction in the usual fashion. You first construct the splitting operator, which is now, I mean, this notation. So this is partially defined K-forms. So K-forms for which all the entries can come from F only. And so you have a splitting operator mapping a section of the homology bundle back to a partially defined K-form. And then you define BGG operators in the usual fashion. And you get the standard results. So if the initial Cartan connection is flat, then this twisted partial deram, however you want to call it, is a complex. And then also BGG or partial BGG becomes a complex. And the splitting operators define a chain map that induces an isomorphism in cohomology. So you get exactly the same results that you get for relative BGGs. But now it's really, you see, relative BGGs, you have fixed dimension of the base and fixed dimension of the fiber. So here it's just the fiber that you care about, and the dimension of the basis is completely arbitrary. Yeah, and finally you get the analog of normal solutions to the first partial BGG operator. So you get everything that comes out of the BGG machinery for free, more or less. Okay. No, thanks a lot. Yep. Infinite dimensional, yes. Yeah, but the partial Cartan geometry is not a trivialization of the whole tangent bundle. It's just a trivialization of a part of the tangent bundle. No, not at all. I mean, you see, if you just think about if you want right? This carries a canonical partial Cartan geometry. And any diffeomorphism of RK with the identity here gives you a morphism of this partial Cartan geometry. Yeah, so since it's not the whole, what you have is always, if you know what happens in a point, you know what happens along the fiber. Yeah, but the fiber is only, so it's or along the leaf of the distribution. That's the right thing to say. Yeah, so on the level of the Cartan bundle, if you know what happens in a point, you know what happens on a leaf of the distribution. That's it.
That's kind of parameterized. Well, right hand side we can modify, right? It's kind of parameterized.
Absolutely,
right?
Absolutely.
Even less geometry and you can also change parameters.
Yeah.
Well, here you can.
Yeah, I mean, this was just for illustration. I mean, you can definitely do something like take a locally trivial bundle and the structure on each fiber in such a way that it depends smoothly on the base point. And locally, the things all look like that. Absolutely. I mean, sure, take a foliation with a dense leaf. Then yeah, say you take a single dense leaf. Yeah, you have one leaf that is dense, and it's the only leaf that is dense. So then I would probably say that maybe I'm wrong. No, I'm not sure. I mean, I haven't really thought about cooking up an explicit example, but I think it should be possible. Locally, you have Frobenius theorem. So locally, it's really like a product of a k-dimensional space with an n-dimensional family of structures. No, sorry. I mean, what I mean is not that they are locally isomorphic. This is not the case. But locally, you really have the picture of a fiber bundle with a smoothly varying family of structures on the fibers. That's what you always get locally. But the tricky thing is globally, it may happen that if you have nasty leaves, yeah. Yep. On each leaf. Yeah. Yes, I think so. I mean, naja, canonically local product. Naja, you see, I think you can just naja. No, I don't think it's deep. I think it should be. I mean, yeah. I think it should be relatively easy. Yeah. Yeah. I don't know. No, I mean, it's the whole story is pretty fresh. So okay. Yeah, this is opposite. Yeah. Ah, okay. Mm-hmm. 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 Yeah. No, I haven't thought in that direction so far. Mm-hmm. Yeah. Yeah, yeah. And I mean, I don't know whether it fits in general. I mean, it definitely fits in the Legendre contact case. And you see, it's a bit tricky because, I mean, this was a strange thing because, you know, originally in the Boston Eastwood book, the whole relative BGG is introduced as 2 BGG along a fiber. Yeah, and when we did the general version of relative BGG, this point of view got kind of lost, and it's also there is a certain subtlety about that, which is like if you think about, say, the simplest case, you have a projective structure along the fibers. Yeah, then the governing group for this projective structure would be something like SLN plus 1. But in the relative BGG machinery, you actually get a GLN plus 1 and not only an SLN plus 1. Yeah, and things like that. So in the relative BGG, there was more the question we were after was, how can you understand this relative bit of the picture from the global bit of the picture? And what you get here is still a bit smaller than the relative picture, but I think you can recover it completely, more or less. I mean, yeah. No. It's really a different story. Yeah, I don't think that so I haven't seen anything that would be really interesting beyond the involutive case so far.